right? So today we're hoping to finish up chapter 1, which is a lot of conceptual stuff. But I'm going to throw a little bit of chapter 2 in there on unit conversion. So you guys might think that you guys are done with unit conversion when you had introductory physics. Now you know how to convert like bushels to like amperes or something, whatever those units are, right? But we're going to actually utilize this thing called a natural unit, which is actually much easier to use for particle physics instead of dealing with meters, seconds, and kilograms. Okay, but going back to what we had on Wednesday, right? So we're thinking about all these Feynman diagrams again, right? So these are the vertices in the standard models. Okay, and remember when a electron scatter off another electron, so you have two electrons coming in. Remember that the time axis is horizontal. The kind of like the distance between the two particles is kind of vertical. It's like R. Okay, right? So the two electrons come close together, they exchange a photon, and they scatter off each other. And remember that we cannot tell the difference, right? Which electron emitted the photon, right? So on the left diagram, really is the top electron that emitted the photon. The bottom diagram is actually the bottom photon. Sorry, the right diagram is the bottom photons that actually emitted the photon. Okay, but in processes that are these such as particle decay, okay, you are actually able to tell which order things happen in, and this is going to have what you're going to do is instead of linking these vertices vertically, you're going to link them horizontally because one event happened another, right? One vertex happens after another. The prime example of this is hopefully some of you guys have seen this in muon decays in your modern physics class, where a muon is observed on the surface of the Earth because of this example of special relativity, right? If there weren't time dilation, you actually would never, you would see like 10 to the minus 4 fewer muons down on the surface of the Earth. And because of time dilation, instead of the muon decaying in 2.2 microsecond in its own frame, if you go transfer over to Earth's frame of reference, it actually lasts 16 microseconds instead. And therefore, you can actually make it most of the way down to the surface of the Earth. So instead of traveling only about 600 meters, it can travel about 5,000 before it decays. Okay. In modern physics, you're just kind of given that, oh, this thing happens to decay in 2.2 microseconds. Like, where does that number come from, right? So that number comes from the decay for this Feynman diagram, for this particular process. So you have a muon here, okay? And this part here, right, the left half, stop doing that. Why is it turning white? This part here, right, is one vertex, right? I'm gonna do a green thing. I'm gonna do it very fancy, right? And then the stuff highlighted in green is another vertex, right? Instead of the exchange of the W that you can't tell between the two, the way you should think about this is that the muon decay into a muon neutrino first, and then a W boson. Okay, since this is a minus, you can even kind of figure out what the sign. If I wanted to, I can actually even say that, well, this is a particle that's coming out. Okay, and in that case, I would actually put a W minus here, right? Okay. And then that W minus actually decayed into an electron and an anti-electron. Okay. So these are two vertices, one after another, linked together, and therefore the muon does not decay straight into three different things at the same at once. It actually has a chain process. Okay. And this is the reason why it takes so long for a muon to decay. So in particle physics, 2.2 microsecond is a long time, okay? Right, we're dealing with things usually on the femtosecond or the picoseconds, okay? All right, so just to show you guys, typically, so this little diagram here, they would denote it as, mu minus, into this little right arrow thing, kind of like what they do in chemistry. If I stole that idea from them, right? To an electron, a muon neutrino, and then a electron anti-neutrino. Okay. Okay. There's an anti-particle version of this, so you can have a mu plus decaying, instead of decaying into a E minus, it decays into an E plus, right? Okay, and then the rest, you just move kind of, it decays into an anti-muon neutrino, okay? And the W actually decays into a regular electron neutrino, okay? Right. So as we already kind of talked about, right? The electron and positrons, or the anti-electrons, are anti-particles of each other, okay? And unfortunately, by convention, this is not the unfortunate part yet. By convention, all the charged leptons that are negatively charged are considered particles. Okay. The reason for that is that most of the stuff around us are made of protons, neutrons, and electrons. Okay. And we're just going to call that matter. Okay. Okay. Hypothetically, there could be a completely other universe or galaxy that could have, instead of electrons, protons, and neutrons, you can have anti-proton, positrons, and anti-neutrons that makes up all the stuff. As long as it doesn't interact with our universe, planets, or its galaxy, they're not going to annihilate each other, right? Because the behavior of particles and antiparticles, the only difference is that the charge is different. But as you probably remember from electricity and magnetism, right? If you have two like charges, it doesn't matter if they're both positive or negative, right? They will always repel. It's the same interaction, okay? This is just a little pet peeve thing. I would have loved that if they, instead of calling these things E plus and then mu plus, I would have loved that they've just put bars above it to indicate that they are anti-particles, right? The little bars always indicates an anti-particle, okay? That would have made me happy, but people don't do it. If I was in charge of the world, I would force all particle physicists, instead of calling it positron, just call it an electron, anti-electrons instead, and just put E on a bar over it. But you can't do this because people will be confused by this, okay? Anyway, okay, it turns out that the protons that are made of quarks also, right? The proton, as I mentioned before, is made up of 2 up quarks and a down quark, plus a bunch of gluons running around. An antiproton, okay, has a -1 charge. The way you make that is that you have an anti-up quark, another anti-up quark, and an anti-down quark, okay? An anti-up quark, right, has a charge. It's basically an up quark, but instead of having a charge of positive 2/3, it has a charge of negative 2/3, okay? And then you have another one that's also negative 2/3, okay? But then the anti-down quark, right, has a charge of positive 1/3, and therefore all this charges adds up to, well, sums up to, -1, okay? Charge, okay, whatever, okay? So the stuff that has 3 quarks in it are called baryons. The stuff that has 3 anti-quarks in it are called antibaryons, or just anti-particles. It is possible for you to make a particle that actually has only 2 quarks in it, a quark and an anti-quark of itself, okay? Okay. And we're going to see how this can happen when we get into QCD, where there's actually happen to be 3 different color charges, and therefore we're allowed to make these 3 quarks, because 3 quarks combined together actually makes it colorless. It's kind of like hence the word color, right? Red, green, and blue. If you combine all 3 of those colors together, you get white, right? You get no color. Okay, but if you combine a red and anti-red together, you also get no color. Okay, so in outside the nucleus and outside the protons and neutrons and mesons, right? The quarks cannot exist outside these places, okay? And this was discovered by these 2 gentlemen, Gross and LectureCh, in 1973, called asymptotic freedom, where it's basically the fundamental theory that describes the interactions inside the nucleus, inside protons and neutrons and all the mesons. And we're going to see a lot more of that when we get to that part of the class in a few chapters. Okay, there are a lot of hadrons. So remember, anything that's made up of like quarks are called hadrons, right? So baryons and mesons combined, the two groups together are all hadrons. Okay, there are so many of these. There's a big giant table of it. Well, actually, not a big giant. There's a big giant book with tables in it. So it's like 500 pages thick. And people have just been discovering these new particles, new hadrons all the time, and measure their mass, how fast they decay, or the behavior. And this is work that's been done in the 1970s when people were discovering a lot of different particles. Okay, and right below here is it's just a little chart. You don't have to worry about memorizing any of this stuff. But I just want you guys to recognize some of the particles in here. Okay, so let's start on the right because there's only one guy over here. So this little n here, right, this stands for a neutron. Okay, a neutron has a very long lifetime. Okay, 1,000 seconds, about 15 minutes. Okay, but so a neutron is actually not a stable particle outside a nucleus. If I pluck a little neutron outside from me, I put it in this room, it'll decay on average in about 15 minutes. Okay, the muon we already talked about. Okay, 10 to the minus 6 seconds, right? So 2.2 times that. Okay, there are other stuff in here. Okay, so this is a K plus, K minus, pi plus, pi minus, right? Those are mesons. Okay, this lambda particle and this omega particle are actually baryons. Don't try to remember which one is which. That's why there's a whole giant table for it. Okay, there are other particles, and the idea here is that all of these particles, the way they decay is through the weak force. Okay, this one also. Okay. Yeah. The way that these particles decay is through the strong force. Okay. Okay. So hopefully you notice the pattern that a strong force decay tends to happen very fast. A weak force decay tends to happen very slowly. Okay. And that's sort of the key thing I want to get you guys to think about in this diagram. Whoops, I circled too many things. A strong force decay, right? Okay. There are electromagnetic decay, which is the pi zero, the eta, and the sigma zero, and that's between the two. And hopefully you see the pattern here also, right? Strong interaction have the largest coupling constant, right? Around 1, okay? Electromagnetic interaction has the second strongest coupling constant, 1/137, right? The weak interaction has the smallest coupling constant, 1/10,000, right? So this is the reason why these particles live longer or shorter, depending on which path they take in order to decay into a lighter particle. Okay. All right. Any questions about this? This is basically kind of what I want to cover in section 1.1. Okay. Something in the chat.
Yeah, there's a question in the chat.
Yeah. Okay. Would you please add up the charges? I don't know how they get. So the pions, they're composite particles. So for example, right, if you have a pi 0, I think technically it's actually an up bar plus, well, there's going to be 1/√2 in front, plus a down bar combined together. Okay. That makes a pi 0. And that's because, well, if you have the antiparticle of itself, this is going to have neutral, this is going to be neutral, right? But if you want something that has a +1 charge, right, how do you make that, right? So an up quark, right, will have a charge of 2/3. So we need something that has the charge of +1/3. How do we find something like that? So this is a pi plus. How do we find something that has a anti-down quark, right? Because the down quark has a charge of -1/3, so the anti-down will have a charge of 1/3, right? Okay. Don't worry too much about details about this, but the general idea is that there are different decays, and the weak decays tends to take a long time. The electromagnetic is intermediate, and then the strong decays are usually the fastest. Okay, and look at this time scale. Okay, it's more important to kind of see this time scale, right? There are decays that happen in 10 to the minus 24 seconds. Okay, so you never see it actually. Okay, all right. Okay, now I'm going to jump into chapter 2 before going into detector stuff, because I rearranged things because I think this is much more important to get through, and I can just kind of breeze through the detector stuff after this. Okay, just so we can wrap up this week. Okay, so remember when we talked about coupling constants, we were just talking about coupling constants. This is actually alpha EM. Okay, this is the coupling constant for electromagnetic interaction. It's also known as the fine structure constant. It was measured somewhere else before people thought about coupling constants and particle physics. All right, this number is the electron charge square 4 pi epsilon naught h bar over h bar c. Okay, and all of these constants here, right? Epsilon naught, h bar, c, right? They are constants that has the right units, right? Charge square, Newton square, and then Joule square and meter square, so that when you put all of this together, all these units together, what's going to happen is that this becomes a unitless quantity, right? And that's nice because this number is always 1 over 137. Okay, no matter what unit system you're using. Okay. In fact, right, the speed of light is really a definition that we decided. Maybe not we, maybe the French did it actually. Because the speed of light is basically how I think it's the second, the speed of light is defined by the meter, right? And a meter is defined by how far light travels in 1 over 3 to the 8 second. 1 over 3 to the 8 second. Okay. Remember this from general physics? This is just some definition. Okay. It's convenient. A meter is nice. I'm about a meter. Tables are about a meter. So a meter is a nice unit when we're working at the human scale, right? But it's not very useful at the subatomic scale, right? Because we're going to always have to 10 to the minus 15, 10 to the minus 20, all that stuff all the time, right? So let's make this unit a little bit easier. And what's going to happen is that things will turn out to be like around 1 all the time, which is kind of nice. Okay, the way we're going to change this unit system is by just making the speed of light equal to 1. Okay, so you can think of it as, oh, well, we're going to reduce the seconds, so it's actually 1 over 300 to the 8th, 3 to the 8th, 3 times 10 to the 8 times what it used to be. So, but the idea is that, right, the speed of light is some length unit divided by some time unit, okay? In fact, if we make the length unit and the time unit the same, okay, don't even call it a second, don't even call it anything, just call it Bob, okay? Bob over Bob is equal to 1, okay? All right, just bear with me, okay? This is probably something that's kind of wonky to do, okay? So if we define the speed of light to be equal to 1 with no unit, okay, right? Length has the same unit as time. It has to, right? Because otherwise they won't divide out, okay? Okay. In fact, in special relativity, when we next week, we're going to see that we have to treat time and space the same way because they are the same. When you're changing reference frame, they have to transform the same way in order for us to have a calculation that is frame independent, or what's also known as Lorentz invariance. Okay. In fact, and similarly, what we can say is that, well, let's not deal with any of these conversion factors, right? Let's make epsilon naught 0, h bar not 0, 1, h bar equals to 1, mu naught equals to 1, okay? And we know for a fact that since this equation up here is unitless, right? No matter what units we use for these things, instead of using Coulomb, we use something else, right? In fact, the electric charge is actually unitless in this unit system, okay? We put all of that, the coupling constant for electromagnetic interaction is still going to be 1 over 137, right? It's not going to change, right? You guys believe me? Okay. Something that's unitless, right? No matter no matter what units you use to calculate it, it's going to have the same number, right? Okay. All right. In fact, we can see is that, well, if we put epsilon equals to 1, h bar equals to 1, c equals to 1 in the fine structure constant equation, what you end up with is that alpha, right, which we know is 1 over 137, with no matter which unit system we use, right? It's going to be the electron charge 4 pi, right? But then h bar is 1, c is 1. So you don't have to write that at all. So in fact, you can actually calculate what the electron charge square is in this weird unit system, okay? In fact, the electric charge is actually unitless also, right? Because there's no units on the right. Pi doesn't have a unit. 137 doesn't have a unit, hopefully, right? Okay. Okay. And this is known as the natural unit system. Historically, it's also known as the Lorentz Heaviside units. They are the same. Well, the one we're using is going to be Lorentz Heaviside unit. So you may see that, but people just refer to them as natural units. Because the reason it's called natural units is that there's no reason a meter is this long, right? There's no reason a second is this long, right? That's just like what we started with, historically, and we just stuck with it, okay? Nature doesn't, care how long a meter is, how long a second is, right? Okay. So, but we do have to pick at least one base unit to kind of keep track of, like, what power of units we're going to have in a particular thing, okay? In high energy physics, we're going to pick this unit called the giga electron volts, okay? An electron volt is the amount of energy for an electron to cross a 1 volt potential, okay? A giga electron volt is a billion of that, okay? Okay. This is a really nice unit because the mass of the proton is approximately 1 giga electron volt, okay? Right. So how do we deal with this unit? So if I have something in meters, right, how do I convert it into my weird, into the high energy natural units, okay? So what you do, just like in, back in first week of general physics, right, you have a unit and you're going to have to multiply it by some conversion factor to get it to a different unit, right? Okay. So, right, the right-hand side is going to have some power of GeV, and this power could be positive or negative. And it's easier to just make it positive or negative versus putting it in the numerator versus the denominator, right? Stuff in the denominator is just negative power, right? Okay. But the key thing here is that we have to divide. Oops, I just crossed it out. That's not the right way to do it. Don't just cross out units, okay? You have to divide out that meter somehow, right? We want to get rid of this meter on top. In order to get rid of that, we have to divide out that meter unit, okay? So we have a bunch of conversion constants, right? C is this, H bar is this, epsilon naught is this. In fact, you can even calculate what epsilon mu naught is, which is the permissivity of free space, right? That's the one that's connected to the magnetic force, okay? And these have these, units here, which is, I'm going to highlight in yellow, okay, right? Meters over second. This one has electron volts times second, or convert it to what we want it at, right? Giga electron volts times second, okay? Some energy times time, right? Epsilon naught has units of coulombs per newtons meter square, right? In the units that we actually want, it actually has units of the elementary charge square divided by giga electron volts per meter, okay? This just this wonky units, okay? Well, don't worry, just you can look all of this up, basically on Wikipedia, okay? So if we want to convert 1 meter, right, into giga electron, some power of giga electron volts, we have to divide out that meter. So we want to look for something that has a meter in it, right? So, epsilon naught does have a meter in it, but I'm going to start with an easier one, right? The speed of light has a meter in it, right? The problem is that if I divide 1 meter with the speed of light, I'm going to end up with a unit of 1 over second in denominator, right? So I have to get rid of that unit of 1 over denominator, okay? So what happened is that, right, we want something that has a unit of meters times giga electron volts, okay? And if you kind of scrounge around and you combine these two together, if you multiply these two together, what do we get? Okay, if we multiply h bar times c together, right? So h bar, I'm just going to write this out, has units of giga electron volts times second, right? A speed of light has units of, let's put to the little bar so I'm consistent with my nomenclatures. Speed of light has units of meters per second, right? These cancel out. So h bar times c has units of giga electron volts times meter, right? Right. Since we want to get rid of the meters, we actually want this in the denominator, right? Okay. So I'm going to put h bar c in the denominator here, okay? And that will convert that a meter, right? This has units of, I'm going to write this out so that you can see this, right? This is giga electron volts times seconds. This is meters per second, right? We used to have a meter on top, right? Let's do the blue pen, right? The meters cancel out. That was the whole point of this exercise. The seconds cancel out, okay? So what happened is that we end up with a unit of giga electron volts in the denominator, right? So, but you don't have to write that in the denominator, just make it, to the -1 power. Okay, so you multiply all that, well, you're multiplying 1. So 1 meter, right, is actually equal to about 5 times 10 to the 15 giga electron volts to the -1 power, okay? So length have a unit of -1 giga electron volt power, okay? Power as in not energy power, but like the power exponents, okay? Yeah. Right. This is kind of neat because, right, remember that the mass of the proton is about a giga electron volts, right? This number here, right? If you convert this to femtometer, oops, let's convert this to femto, oops. If you convert 1 femtometer, remember 1 femtometer, femto is 10 to the -15. So a lot of you guys may not have, people don't usually use that a lot, right? So that 10 to the -15 basically kind of knocks out this power, okay? So 1 femtometer is basically 5 electron volts to the -1 power, right? And the reason I bring this up is that, well, a femtometer is actually approximately the size of a proton. I think it's actually about 2.3 or something like that. It's a little bit less, right? So all of these numbers works at about the same scale, okay? Which is really nice. Okay. What about mass? Oh, so before we go to mass, okay? So lengths have units of inverse GeV, okay? So time also have to have the same unit, right? Because we have to treat time and space the same way, or that the speed of light is 1, so therefore they have to have the same units, right? Either argument works, okay? What about mass? Anyone think about what principle we can use to think about what units will be appropriate for mass? It's the kilogram. Anyone on Zoom, especially? I'll take a little drink. What's one of the most famous equation in the world?
Bahare mentions energy as an option.
Energy. Yeah. Well, let's not think about like, well, it is, you're gonna, okay, Merlin, you're almost right. There you go. You're missing that C. Okay. E equals mc squared, right? Actually, that's not the right equation, by the way. Every time I say this to people, people stare at me as if I'm crazy because, why would you disagree with E equals mc squared? Everyone knows that E equals mc squared. So technically, it's actually E equals gamma mc squared, right? Because the m here stands for the rest mass. And then if the particle is moving, you actually have to account for the Lorentz factor. And we'll get into that next week, okay? So in this case, while the Lorentz factor is unitless, has units of 1, if we make C unitless also, right, energy and mass have the same units, okay? And we already have a unit for energy, right? So for the kilogram basically change into the same units as energy, or Becquerel just say in GeV, okay? In fact, if you go a little further, if you want to figure out the units for momentum, okay, we can use the Einstein energy momentum relations, and we're going to review this next week, right? E squared equals P squared M squared. Notice that I don't even say the C anymore, right? Because I'm so used to just having C equals to 1. So energy, momentum, mass, they all have the same units, okay? So hopefully a lot of you guys seen this little table. This is a super useful table. I wish I had this table when I was taking this class. I didn't have this. So this is a big table of all the different, some of the quantities that you're going to see most often. Okay, energy, momentum, mass. Okay, and then what they are in SI units. Okay, and how do they get converted to GeV? So if you want to convert time from second to inverse GeV -1, you just basically divide by h bar. Divide by h bar. Okay, and that'll get you that conversion. I think, yeah, you divide by h bar. Okay, okay, and that'll allow you to leave that with the GeV -1 power. Okay, and we're gonna, yeah.
So if you want to convert, just take the second, divide that by h bar.
Right. So 1 second, right? So h bar has this units up here. What was the number up here? H bar is this GeV per, 6.6 10 to the minus 25, right? So if you multiply this by 6.6 times 10 to the minus 25 GeV inverse second. Okay, so you want to divide it. Okay. Did I say multiply? Oh, there's a
Hey,
negative one
Wing,
here.
we
Yeah, go
couldn't
ahead.
really hear the local question. Can you repeat
The
questions?
question was that
Who are
if you
there
want
with
to
you in
convert
person,
one,
ask questions?
sorry, yeah, I should do that. Thanks for reminding me. Yeah, if you want to convert a second to natural units, how do you do that? Right, so 1 second here, right? We want to cancel out the second. Therefore, this number here is actually h bar, right? That has, this second here. That's why you can cancel this out. Oops, there's not a -1 here. Okay, and therefore, when you multiply this number together, then you have something. I don't know what that number is. You can punch in a calculator with GeV -1 power. Okay, yeah. So this table is super useful whenever you want to convert units. Basically, look at that table, and that's what you multiply by in order to convert it. Okay. All right. So, and there's going to be like 3 homework problems on this, and it's like the end of the homework problems. And hopefully we get a bit of practice of that. When is the homework due, by the way? Is it Sunday? Okay. Let me know if that's like super hard, because I know we're just covering this stuff right now, and you don't have your weekend free, then that's going to be pretty hard. Okay. Okay. But what we'll do is we'll actually do a peer review of the homework on Monday if everyone's able to get this done. Okay. All right. Okay. Any questions on natural units? I went through it faster than I wanted to because there was a couple of other examples, but it's in the book, so hopefully you can just read it instead. Okay. Okay, and there's 3 homework problems to practice also. Okay, so what I want to finish up today is basically the end of the first chapter, which is going to be like on detectors and how do particles actually interact with matter. Okay, so if you have some sort of particle, this is an example. Let's call it. Let's just make it an electron. Okay, and it's zooming around in free space. Nothing's going to happen to it, right? But let's say it hits a little bucket of water. Okay, what's inside water? H2O. That's a very chemistry way to answer that question. What's inside H2O? Oh, sorry, the answer was H2O here locally. Okay. But what's inside H2O? If you go down to the 10 to the minus 15 meter at the femtometer level, what's inside that? Protons and electrons. Okay. So this is the way we're going to start thinking about things at the fundamental level, what we can describe, right? Okay. What happened is that, right, the electrons this electron here can bounce off another electron, right? We did that with Feynman diagram. Or it can bounce off the protons and nucleus also, okay? So what's happening is that when this happens, okay, especially when this electron, we're going to start off this electron bouncing off another electron. When the 2 things exchange a photon between them, okay? This second electron, I'm going to draw in a different color. Sorry, should do this. Make this red. Okay, make this black. Okay. What happened is that the red electron maybe bounce off this way. Okay. The black electrons, you can't really in real life tell the difference between them. It's going to gain some energy and can maybe get bounced off, basically get it removed from the atom that it used to be bound to. Okay. This process is called ionization. Okay. Okay. I probably should have made this drawing over here because I saved space for myself for no reason, I guess. Okay. And ionization is the primary way that electrons and muons interacts with material at a particular energy range. Okay. In this kind of lower energy range. Okay. Okay. And so what I'm going to do is I'm going to show you guys this plot even before the equation, because the equation is just going to be confusing. This is known as the beta block plot. Let's not even call it an equation. Okay. What's described here is how much energy dE, dx, how much energy is lost by the particle as it travels through a particular material, maybe helium gas, carbon, iron, lead, right? And these different lines. Okay. They're also going to divide 1 over density. We're going to figure out what the situation of density here is. So vertical axis is how much of the energy gets lost. Okay. That's what you want to think about. Okay. The horizontal is a little bit more complicated. This is one of the reasons I'm going to have a different plot to show you guys in a second. Okay. Is beta times gamma. So we're going to jump into relativity soon, right? So beta is the speed of that particular particle divided by the speed of light, or the fractional speed of light, okay? Since we're going to be using c equals to 1, so beta is the velocity, okay? And it's always going to be less than 1, okay? If you discover something that's bigger than 1, let me know, then I can get credit for it, okay? All right. I remember gamma, right, it's 1 over square root of beta. Alex, remind me, is that just beta down there? I forgot. Okay. It's okay. We don't have to get all these equations right. Okay. I think it's just beta down there, right?
I
Yeah.
have to think, I never write things in terms of beta. I mean, beta is just V over, no, it's beta squared. Yeah.
Beta
Is that
squared,
what
yeah.
you're asking?
Yeah. Yeah.
It's beta.
No,
yeah,
I was
beta
asking if
squared.
it's actually beta. Okay. Or some other stuff in front of it. Yeah.
No, yeah, nothing else.
Yeah. I mean, yeah, usually I think people will write this over b squared over c squared. Okay. But
Yeah, that's how I always do it.
that's
'cause
more
it seems
people are
always
used
silly
to
to me.
Okay. So this is some weird thing that has to do with like how fast the thing is going, right? Or maybe you can think about it as how much energy that particular particle has, right? The faster it goes, the more energy it has, right? Okay. So we're just going to look at this kind of like conceptually, right? So at low energy, not energy, low energy, right? The particle is going to lose a lot of energy per, per units of length that it travels through that material. Okay. So anything that's slow, okay, if it tries to go through a particular material, it's going to lose most of its energy, get stuck in that particular material, and it'll just be stuck there. Okay, unless it decays or something. Okay. So this is the low energy particles are sticky. Let's just say that. Okay. High energy particles are also sticky. Okay. This is the high energy, right? So faster they go. Okay. 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 And the reason we can think about that is that, well, if the charge has a high energy, and this only applies to charged particles. That's why it's the muons and electrons that I'm saying, okay? Neutral particles doesn't interact with the electrons, right? So it just passes straight through, okay? High energy charged particles have larger momentum. So every time it interacts with an electron in the material, it gives it more energy, right? So it makes sense that low energy stuff are sticky because the slower you pass through the material, the more chance you have to interact with the electrons in there, right? High energy particles also are sticky because, or doesn't penetrate as much because, right, every time it interacts, it gives out more energy. So it makes sense that there's going to be a little trough in the middle here, right? In the here. And this is a very special place. This place is called the minimal ionizing energy. Ionizing energy. Okay. And it happens at, around a beta times gamma of around 2 to about 6. Okay. Okay. And this plot comes from this fancy equation called the beta block equation. Okay. Don't even read it too much. Okay. We'll describe. If you actually need to use this equation, you'll have to figure out what these alpha, all these H bars and stuff like that should go away. You don't need that, right? Because they're all one. You have the mass of electrons and all that stuff. Okay. Okay. But the thing I want to bring up is that this is often plotted as the amount of energy loss per length divided by the density of the material. Okay. Okay. Because what happened is that, notice the unit here, right? The unit here is MeV per gram times centimeters square. Okay. So what is the unit of density of a material? Usually in SI unit, let's say. Mass over volume, right? So that's the answer from local, right? So kilograms over meters cubed, right? But since we're using grams here, so we can use grams over centimeters cubed. I can write that. Okay, right? This unit will cancel out. Most of these units will cancel out. This is actually MeV per centimeter. Okay. Okay. This is how much energy that particular particle would lose per centimeter it travels through that particular material, right? So that's why this plot is not going to give you exactly the energy that loss per length. You have to multiply by the density of that material, okay? And that's basically the only point I want to get across here with this equation. Don't look at the right side here, okay? Okay, this is really complicated, okay? And there's a reason why all this stuff is in there. In fact, if you were to make that same plot with muon, and let's just deal with copper so we don't have 4 different lines, okay? You can remake the horizontal axis instead of just dealing with beta times gamma, right? Once you know that it's a muon, you know the mass of that particle. Once you know the mass of that particle, you can actually convert beta times gamma into energy, right? It's how fast it's moving. If you know how fast it's moving, right? In classical mechanics, it'll just be 1/2 mv squared, right? Okay, but similarly in relativistic, but it'll be a slightly different equation because of the gamma factor. Okay, so this is to me easier to understand. So if you were a muon and you want your muon to be this minimal ionization regime, right, between a gamma beta gamma of 3 to 6, right? Your muon should be somewhere. So this is 1 GeV, this is 1 TeV, this is 1 MeV. So this unit here is actually MeV, okay? So you want your muons to be a few hundred MeV. So, oops, let's just, right, hundreds of MeV. And that actually is where the muon loses the least amount of energy per distance travel, okay? If you go lower energy, it'll lose more energy. If you go higher energy, those muons will lose more energy. Okay, that's sort of what the thing I want to get out of this plot. Okay, don't think about the equation, just ignore it. Okay, think about the units on the equation. That's it. Okay. Any questions about this? Okay. Okay. So ionization is one of the fundamental way for us to detect charged particles. Okay, that are at a okay. So for in high energy physics, these will be considered low energy muons. Okay, a GeV basically travel almost about 3/4 the speed of light. That's considered very low energy. Okay, what you can do with this is that you can make tracking detectors out of it. Okay, so remember that the original picture I draw up top, right? You have a little bucket of, let's not do water this time. let's say you have a bucket of silicon, okay? Silicon, okay? It's actually a solid at room temperature, so, and you have a particle passing through it. Let's make this a muon, okay? As it passes through it, what's going to happen is that it's going to ionize the material a little bit, right? That's the idea. It's going to hit that electron, knock it out of its orbit, okay? Okay. If you were to do this, right, in silicon, what's going to happen is that you're going to create these charge hole pairs. So the positive is actually the lack of an electron in one particular atom, okay? Because if you take a neutral silicon, right, normally it's neutral, but if you take one of the electrons away, it actually has a positive charge, okay? And in electronics, these are called holes, okay? What's going to happen is that you can put a voltage across this, okay? If you're not used to voltage, you can just think about this as an electric field, right, across this. And then the positive charge will actually get pulled upward. The positive holes will get pulled upward, and the negative charge will get pulled downward. And you can actually read this out as a signal. So therefore, you can actually detect whether or not a muon actually passed through it, okay? So this is a yes or no question, right? Muon. And you don't even know the charge. Questions? It's not doping, it's a little bit different, yeah. Yeah, this is just us shooting things into a material and causing the electron to get ionized away from the atoms. So therefore now the atom is actually positively charged, okay? Question online? Okay, okay, so there may be some problem with the sound. The question and Oko was that is this has related to doping of semiconductors, and it's not. It's a slightly different thing we're doing here. Okay. Okay. So why are we doing this? Okay, because you can. I mean, I can tell whether or not a muon passed through something or not, right? That's what this detector is designed to do. What you can do is that you can actually have multiple layers. So each of these is a layer of silicon, you know, in a sheet. Okay. What happened is that if you have a particle travel, if you have a muon, let's just make it a muon traveling through here, you can say, oh, I found a muon here, found a muon here, found a muon here, found a muon here, found a muon here. With this, you know, list of positions, you can actually track where the muon is going, right? So that's why these things are called trackers, okay? And it's a very creative name, okay? The curvature here, okay, is due to the fact that if you want to build the tracker and you want to measure the momentum or how fast this muon is going, okay, you put that muon in a magnetic field, okay? If you have a charge in the magnetic field, right, you're going to have the Lorentz force on this. The Lorentz force is actually relativistic, by the way. This is perfectly good, and you don't need to change this. I think so. Dr. Miller might tell me that I'm just completely wrong. I think I remember this is actually a completely good relativistic equation. You have to define like what force actually mean relativistically, but yeah. So what happened is that as this muon travel through, I'm going to draw that in red, okay? Your tracker, if you put a magnetic field, for example, into the board here, okay? Once again, you use your right, people remember the right-hand rules of general physics, right? If you want to figure out what the force is, you take the first vector, this is your index finger, I think, right? And this is your middle finger, and this is the direction of your thumb, right? Okay, so the velocity is going, well, unfortunately people can't see me, the velocity is going this way, right? The magnetic field is going into the board. If you use your right-hand rule, you're going to see that there's going to be a force pulling it this way. So that's why this particle curves the direction it does, okay? All right, so that's one of the type of detectors. So let's not go through a lot of this. You can, okay? There are other types of detectors or other types of interaction that allows us to figure out whether or not a particle went through our detector or not. The second one is called Bremsstrahlung. Basically, so remember that the ionization is kind of like the moderate energy stuff, okay? Bremsstrahlung, this is when you have very high energy. The reason for this is that it's high enough energy so that instead of just the electron scattering off the atom, when it scatters, it actually can produce an extra photon. Okay. Or, right, a photon can scatter off the atom, and then instead of just producing a photon, it actually can produce an electron and positron pair. Okay. So the mass of an electron is about half an MeV. So in order for this to happen, you need to have photon energy that are above 1 MeV, right? So this is very high energy interactions that's happening, okay? In fact, what can happen is that if you can have an electron produce a photon, and then a photon that can produce electrons, right? You can actually have a cascade of events that's happening, right? Photon 1 produces electron 1, right? Electron 1 produces photon 2, photon 2 produces electron 1, right? It just keeps going, okay? And these are called electromagnetic showers, okay? Okay. And this is how basically a detector are able to detect photons and electrons, okay? I'm gonna try to do one more thing before we wrap up. I know I'm over by a minute, okay? There is another type of interaction, okay, where instead of a photon or an electron, okay, let's say you have a proton or some sort of charged meson, such as a pi plus or pi minus, okay? Okay. So at low energy, right, so a proton is just kind of like a normal, just like another charged particle. So you could have ionization there also, right? But at very high energy, what happened is that it will actually start interacting with the nucleus of the, whatever material. So usually it's like lead or iron. So you're actually starting to interact with the nucleus itself, okay? And that at high energy, that's actually what's going to be the interaction that you're dealing with, okay? So if you want to detect protons and charged mesons or other hadrons, okay, you actually want to use these things called hadronic calorimeter. Hopefully that makes sense. And the word calorimeter, those of you who haven't had thermal or a chemistry class, calorimeter, or cannot spell calorimeter, is basically a way to measure energy, okay? Right, not energy, okay? So, and this is kind of the detection method that most of particle physics use in order to detect things, okay? Either ionization, I'm just gonna list it here so I can write it down. Ionization, okay? This tends to be low energy, okay? Okay, Bremshelon, Brem, I probably won't be able to even spell it. Brem, I'm not gonna try to spell it. It's gonna be hard. There's an H, random H somewhere. Okay, this is high energy, photons and electrons, okay? Okay. And then there's hadronic interactions, okay, which is high energy. Oops, I said low here, didn't I? This is high energy. I wrote low, but I meant high, right? Hadrons, okay? Okay. Okay. And sorry for going over a little bit, but I'm going to stop recording here. If there's I can stick around for a little question if anyone